The UFS webinar. This webinar is hosted by the National Weather Service and the Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. I'm Shira, and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar in the future, you can email their recommendations to ufs.modeling@noaa.gov, and we will take your suggestions into consideration. Due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them on the Google document that will be provided momentarily in the chat box. Presentations will last about 45 minutes, followed by question and answers for about 15 minutes. Type your questions onto the Google document that I will post in the chat box during the presentation. Today's presentation is a new operational hurricane prediction system for NOAA. UFS-based hurricane analysis and forecast system. Today with me, I have Dr. Vijay Talapragada to introduce our speakers, so I'm going to hand it off to him. Vijay, go ahead. Thank you.
Thank you. Thanks for the opportunity to introduce two distinguished speakers today. My name is Vijay Talapragada. I'm a senior scientist from the Environmental Modeling Center, National Centers for Environmental Prediction for Weather Service. And I'm glad to introduce my colleague, Dr. Jian Zhang, and also a collaborator, Dr. Shujin Zhang. Jian Zhang is the hurricane team leader at EMC. He has 25 years plus experience in model development, tropical meteorology. We both overlapped for a while at Florida State, so I know him for such a long time, and has been extremely productive scientist in terms of working on various problems, including the development of the previous versions of hurricane models, the HWRF and the HMON, and has been leading the effort in terms of building the models for operational transitions. He is also specialized in ensemble forecasting, and he has been producing hurricane ensemble forecasts as part of the HFIP real-time experiments for such a long time. So very important contributions for improving the hurricane model forecast skills, and working with our collaborators, especially from HRD AOML, where Dr. Shujin Zhang is working. And I know him very well since he joined HRD as a model developer. I've been working with him in the development of HWRF in the previous generation, and in the recent times, the new UFS-based hurricane analysis and forecast system that you will be hearing a lot in the next 45 minutes or so. So this effort of developing the HAFS is supported by the Hurricane Supplemental Projects and the HFIP and the UFS R2O project. So it is a true collaboration that's working among the community of hurricane modelers and developers working together to develop a brand new operational system from scratch and implement it in a record time of less than 4 years since the project has begun. So huge compliments to both Jian Zhang and Shujin Zhang and the hurricane team that has worked tirelessly and produced 2 versions of HAFS that got implemented a couple of weeks ago on June 27th. The new models have been implemented, and you will hear a lot. Again, I don't want to steal thunder from them, but the point is this is a model that Unified Forecast System has adopted, the community-based model development, and you will see a reflection of how using the common tools and infrastructure to build applications has worked, and transitioning the legacy applications from NSEP production suite into UFS-based applications to minimize the number of distinct applications that we are running in operations. So I will let Jan Jiang take over and start giving his presentation, followed by Shujin. I believe he will tag along somewhere in between. Go ahead, Zach.
All right, so how do I share my screen, or can you see my screen?
Well, you see your desktop. Go ahead, share your screen.
Yes, I did. Do I have to share, or I guess the host need to share my screen, right?
Yeah, let me give that back to you, Zach.
It's already my slide is already on my screen, the desktop. Okay. Can you see my screen now?
Yeah,
Yeah,
looks
good
good.
now.
All right. Okay. Thanks, Vijay, for the nice introductions. And also thanks for the UFS webinar for the opportunity. Good afternoon, everyone. And so I will jump to the presentation right now. And so what we are going to, Xujing and I are going to talk about the new hurricane system, which is hurricane analysis and forecast system we call HAFS, which was implemented operationally 2 weeks ago. So HAFS is a collaborative and community-based project, which involves many developers from different organizations, different NOAA organizations, and also different expertise. And I would like to first acknowledge all the contributors listed here. And without all their contributions, we would not be able to achieve what we have achieved now. So before I jump to the HAFS development, I would like first to quickly mention that there are two existing operational hurricane prediction systems: HWRF, hurricane weather research and forecast, and HMON, hurricanes in multi-scales, ocean coupled, non-hydrostatic. So both systems are on-demand system, and HWRF is actually running for the storms in all global oceanic basins. And HMON is only provide the storms for forecasts for the NHC area of responsibility, which is North Atlantic basins and East Pacific basins. So now I'm going to first to give a brief overview of HAFS. HAFS is a UFS-based hurricane application, which is uniquely designed for to provide a tropical cyclone track and intensity forecast guidance using atmospheric ocean wave coupled forecast system, and with convection allowing high resolution moving nests, Vortex initializations, and inner-core data simulation, and also the model physics that's specifically designed for hurricane applications. So we started HAFS project in 2019, and the project was jointly funded by NWS and OAR. And HAFS developers include all the scientists from different NOAA organizations and research communities, and also many universities. So we have been running HAFS system in real time for the past 3 years, from 2020 to 2022, last year. So finally two configuration of HAFS became operational, as Vijay mentioned, on June 27th, 2023. And the project is now extended. The UFS R2 project is extended, and phase 2 is being planned. So the scientific objectives of HAFS project are aligned with NOAA's another project, Hurricane Forecast Improvement Project, HFIP, which uses 2017 forecast skills as a baseline. And the goals includes to reduce the track and intensity forecast guidance error by 50%, to provide to produce 7-day forecast model guidance as good as 5-day model guidance compared to 2017 forecast, and also to provide improved tropical cyclone genesis forecast guidance by 20% in terms of both track intensity and rapid intensifications, and also finally to improve the hazard guidance and risk communications based on social and behavior science studies. So now I'm going to talk about the scope of HAFS version 1 upgrades. As you know, HAFS is a brand new model system and is totally different from the current hurricane model system as of like HWF and HMA. The red items are the innovative features in HAFS that's implemented for the first time in operation, and the others are the upgrades on top of existing algorithms or schemes. So I will elaborate each of the upgrades in the next few slides. So in terms of system and infrastructure upgrades, HAFS uses FV3-based dynamic cores and CCPP-based model physics. CCPP stands for Common Community Physics Package. HAFS has the moving nest capability in the dynamic core, in the FV3 dynamic core framework, and other upgrades includes the model efficiency improvement, that's so that we can fit the runtime in the operational time windows, and also a new workflow that's designed for hurricane applications. So, and the Vortex initialization is an important component in the tropical modeling system. The VI in HAFS is leveraged. The VI schemes in HAFS is leveraged and modernized from HWF and HMA. The VI threshold for the warm start in HAFS is tuned and adjusted compared to HWF and HMA to provide improved initial conditions based on JFS V17 input. So the figure at the right are showing that both track and intensity forecast guidance that I actually improved with the upgraded warm start threshold compared to the current operational system HWF. And in terms of the DA upgrades, similar to HWF, DA is only applied for the nested domain in HAFS. And the main upgrades in HAFS for the HAFS upgrades, HAFS DA upgrades is that HAFS is using 4D ENVA with the GDS ensembles, while HWF is using 3D ENVA. Our experiment showed that the 4D ENVA can further improve the TC initial conditions and have a very positive impact on both track and intensity forecast, as you can see in the right side. And the coupler in HAFS is upgraded from NCAP coupler to the synapse-based coupler. Synapse stands for Community Mediate for Earth Prediction System. And unlike HWF, which is coupled with MPI palm ocean models for NHC basins, HAFS is coupled with HICOM for all global oceanic basins. And the model domain is also extended to cover the entire NHC basins, including North Atlantic and East Pacific basins, to reduce the impact of non-overlap areas between the atmospheric and the ocean domain. And other minor upgrades, including vegetation type upgrades and wave model upgrade. So model physics advancement, HAFS is using new microphysics schemes. For example, uses both GFDR and Thomson microphysics, which I talk more in the next few slides, in HAFS, while HWF, HMA are using very illegal microphysics schemes. And also we upgraded all other model physics schemes like TKE-based EDMF PBR schemes and GFDR, GFS surface schemes, and also scale well convection schemes and gravity wave drag parameterization schemes. And on top of all these upgrades, physics parameters are also adjusted and tuned for the hurricane applications. For example, we adjusted mixed length scales in PBR, and also the deep convection entrainment parameters in the current convection scheme. So after testing and testing various, all different configurations and conducting numerous experiments, we have finalized the two HAFS configurations, HAFS A and HAFS B. HAFS A is going to replace the HWF, and HAFS B is going to replace HMA. The color item indicated here is the differences between the two configurations. And as you can see, the domain coverage and the resolution are very similar between the two schemes, between the two configurations. And you can see 2 kilometer horizontal resolution for the parents domains, and 6 kilometer for the parents, and 2 kilometer for the nest domain. And we have 81 vertical levels with 2 minimum model top. And as I mentioned, the VI vortex initialization threshold are slightly different between the two configurations. And also both configurations are two-way coupled with HICOM ocean models. But HAFS A is also one-way coupled with Wave Watch 3 models. And also you can see the main differences between the two configurations are model physics, which I will show in the next slide. So this table lists all the physics schemes used in HAFS version 1. So suite 1 is used in HAFS A configuration, and suite 2 is used in HAFS B configurations. And also the color item indicated the differences between the two model physics suites. You can see the microphysics are different, and also the PBR scheme are also different, and also other minor differences in the convection schemes. So I'm going to talk about the HAFS version 1 development strategy. It's actually the same strategy we used to upgrade the HWF and HMA in the past several years, in the past 10 years. So what we do is that we first use this current system as a benchmark, this time HWF and HMA. And in phase 1 development, we establish the baseline by conducting retrospective runs using the basic configurations for all storms in the past 3 years at both Atlantic and East Pacific Basin. So phase 2 is the most important phase, development phase. What we do is we conduct lots of small experiments with incremental upgrades for selected priority storms. The incremental upgrades could be any small upgrades, including like dynamic upgrades, data simulation, vortex initialization, ocean coupling, like physics, also all the physics, various physics schemes, and so on. And in phase 3, we selected promising upgrades in phase 2. Then we combine them to finalize the configurations. And then we freeze the code, do the full scale experiment again for the past 3 years, the storms in the past 3 years. So that's how we finalize the configuration, HAFS configuration. So now I will present HAFS version verifications for the North Atlantic based storms. First, for both later and earlier models. In case you don't know the concept of later or earlier models, the later model guidance is the track and intensity forecast from the current cycles. And the earlier model represents the forecast from the previous cycles that are interpolated, then shifted forward in time by 6 hours. This is normally NHC forecast. Typically, they uses the earlier model guidance because the later model forecast guidance is not available to the forecast in time. And the color text indicated here just where represent the models throughout all the rest of my presentations. So HWolf will be shown in purple, H1 will be shown in green, HAFS A will be cyan, and HAFS B will be shown in red. So this slide is showing the verification results for the North Atlantic basins, 3-year retrospectrons, which include lots of cycles, total about 1,091 verifiable cycles. So the top two figures are the track and intensity arrows in the aerospace, and the bottom two are the same, but in the scale space using HWolf as a baseline. As you can see that both HAFS configurations improve the track forecast skills compared to the HWolf with more than about 10% between day 1 to day 4. And improvement in intensity forecast skills are close to about 10% for the lead time beyond the day 2 for HAFS B, and about 5% maximum for HAFS A. And we also noticed that there are some issues in the initial time, which is showing some kind of initial intensity spin up and down issues that we will continue to work on it to improve the model's performance. So regarding the intensity bias, there are slightly improvement in maximum wind and mean sea level pressure bias comparing HAFS A and B with HWolf. You can see HAFS is for the Vmax, it's between the HWolf and HB. It's much better than compared to HMAN, but still slightly improved over the HWolf. Now, as we all know that strong storms causes more property damage and threaten to human life than the weaker storm. So we also did the verification for the storms stronger than 50 knots. As you can see that both intensity arrows and the bias are reduced for HAFS A and B for the stronger storms after like about 36 hours as compared to the HWolf. Now let's look at the earlier model verifications. This is actually further confirmed that it confirms the similar significant improvement in track forecast skills at all the forecast lead time as compared to the same early model versions of HWolf. And also you can see about 5 to 10% intensity improvement depending on which HAFS configurations you're looking at. HAFS B actually performed a little better than HAFS A. So if we add the NHC official forecast, you can see that HAFS forecast skills is actually closer to the NHC forecast compared to HWolf, but you can see there's still rooms for improvement if we compare with the operational NHC official forecast. Another verification matrix to compare two model performance is to look at the frequency of superior performance. And HAFS configurations, actually, you can see HAFS configurations, both HAFS configurations outperform the HWolf in both track and intensity forecast. What you can see here is that basically the blue, which indicated the HAFS bar, is actually higher than the red bar, which is the HWolf performance. So we also do the storm size verifications against the best track. It indicates that HAFS configurations improve the 50 knots and 60 knots wind radii, but showed some kind of neutral impact on the radius maximum ones. It's actually improved over HMount, but still kind of slightly behind HWolf, and also mixed the impact on the 34 knots wind radii. HAFS improved the 34 radii wind bias at early forecast lead time, but kind of have a negative impact on the R34, which produce a relatively smaller storm size, especially for HAFS-B compared to HWolf. So both HAFS actually produce a smaller storm size. So this slide shows the HAFS produce a very similar wind pressure relationship compared to HWolf. You can see actually the orange line and the purple line, actually both lines actually on top of each other, and the black line is here is the best track wind pressure relationship. So for the rapid intensification verifications, which is normally it's important for the hurricane model forecast, so we use two methods. The right two figures are the ones that we use the traditional way to compare the model outputs with the best track for the rapid intensification cycle only, in which HAFS track forecast errors are lower than HWolf and HMount, but the intensity forecast errors are slightly larger than HWolf. The left figure is showing that the rapid intensification RI performance diagrams, which actually confirm that HAFS is slightly behind HWolf in terms of RI forecast. So now we are going to look at the verifications for the East Pack storms. So we run basically we run about 3 years and around 1,000 cycles. So this is the later model track and intensity forecast again for the East Pacific. In general, track forecast skills are positive for almost all the forecast lead time you can see, except before forecast 12-hour forecast for both configurations, with about 5 to 10% improvement. Intensity forecast skills become neutral and then turn to the positive after day 1, and about 10% more skillful than HWolf at day 5. Due to this is actually also you can also see the spin up, spin down issues around before the day 1. So again, the Vmax bias in HAFS actually improved compared to HWolf, and minimum sea level pressure bias are also improved over HWolf, but kind of slightly behind HMount. So looking at the earlier models forecast for East Pacific, it shows very similar results as later models, like about 5 to 10% track improvement at all forecast lead time, and HAFS-A has a positive impact on the intensity forecast, except for forecast hour 48 hours. That's the only degradations we can see at the forecast lead time. And HAFS B actually outperformed HWolf after 48. And again, if we add the NHC official forecast, then we can see that HAFS is actually closing. We are closing the gap between the dynamic models and auto NHC forecasts. And in terms of track, in terms of intensity forecast, that actually you can see dynamic models performed similar or even better than NHC forecast after day 2 for the East Pacific basins. And again, the frequency superior of performance for the East Pacific storms. You can see that at most of the forecast lead time, HAFS configurations performed much better than HWolf, which means that the blue bar is higher than the red bar. And for the stronger storm verifications, storms stronger than 50 knots, intensity errors are reduced for HAFS A, both HAFS A and HAFS B configurations at all forecast lead time compared to HWolf. And also bias also improved for HAFS A. And we see the improvement at early forecast lead time, but degradations at late forecast lead time for HAFS B. So in terms of storm size errors, you can see unlike the North Atlantic basins, the storm size errors for all four categories of wind radii actually improved over HAFS improved over HWolf. Again, the pressure-wind relationship is also actually improved, especially for the stronger storms. You can see the orange line is much closer to the best track, which is the black line, and compared to the purple line, especially for the strong end of the wind pressure relationship line. And for the RI events verifications for East Pacific storms, track forecast skills actually better. For HAFS configurations, they have lower errors. And again, the intensity errors are kind of similar and behind the HWolf and HMON, especially at the later forecast lead time. However, if we look at the probability of detection and the POD or FAR false alarm ratios, the RI performance diagram, you can see actually HAFS is improved compared to HWolf and HMON. So looking at the verifications for all storms and cycles in combined NHC basins, which means we combined both North Atlantic and East Pacific cycles, you can see we have a large sample size by combining the two configurations, two basins. You can clearly see that's about 10% track skill improvement and 5 to 10% intensity forecast improvement over HWolf. So continue with the JTWC basin verifications. Because of the limited computer resources, we only run 2-year recharge spectrums with some selected important storms for JTW basins. JTW basins including the North Atlantic, West Pacific basins, North Indian Ocean basins, and the Southern Hemisphere basins. So this is 3 basins: West Pacific, Southern Hemisphere, and the North Indian Ocean basins. What you can see that HAFS did a pretty good job in terms of track and intensity forecast for West Pacific and the Southern Hemisphere storms. The left side 2 columns, about 5% track intensity forecast improvement for West Pacific and about 10 to 20% track improvement for the Southern Hemisphere storms. And somewhat neutral to positive intensity forecast. It's actually neutral at the early forecast lead time and improved at later forecast lead time for both West Pacific and Southern Hemisphere storms. And for the sake of the completion, we also did some North Atlantic verifications, but the sample size are very small, so it's difficult to draw any conclusion. So in the next few slides, I will show some case studies to highlight some of the HAFS model features. So, this is a case studies that compares the model storm structures of Hurricane Ian 2022. At the top panels is the model output with the flight level observations. Actually, this is NOAA P3 and tail Doppler radar TDR observations, which shows that HAFS is able to produce similar storm structures as the observations, and also model could actually correctly capture the eye wall replacement. And this is another example, case study examples that shows the ocean response. This for Hurricane Fiona 2022 again, and you can clearly see the cold wake was induced along the storm track, which means our model ocean response is correctly responds to the storm track. And comparing HAFS HICOM output with the sail drone observations for Hurricane Fiona, you can see HAFS actually did a good job to predict the relative humidity and the salinity, but somehow HWolf produced a better air temperature and sea surface temperature that's close to the observations. So basically, this is basically due to the fact that HAFS is coupled with HICOM and HWolf is actually coupled with MPI POM. So they coupled different ocean models, and also somehow sail drone observations may not be well calibrated for the temperature observations. And also, as I mentioned, HAFS A is when we coupled with wave models. So we also check the wave output, the significant wave height. We compared the wave height with the buoyancy observations, which showed that significant wave height from HAFS A are equivalent or much better than compared to HWolf and JFS. You can see that it captures the peak wave much better than JFS and HWolf. So this is the score tables that summarize what I have just presented. The green box indicates the HAFS improvement over the HWolf, and the blue box indicates HAFS has a neutral impact compared to HWolf, and the orange box actually indicates that somehow we need to further improve the HAFS performance, which is rapid intensification performance. In general, you can see that the green box actually dominates the tables. I guess with that, I will stop here, and Xujin will continue to talk about the future plans for HAFS. Xujin, okay. Go ahead.
Thank you, everyone, to attend this webinar. So I'm going to present what is the next step. Zach already presents the results, and it looks, it's moving forward compared to the previous operational model. What is the next? So next we focus on 6 aspects. One is the moving nest capability. Will continue develop the moving nest capability with multiple stone, can zoom in multiple stone. Then we also make the model can do a more flexible refinement, which right now is 1/3. Now in the future we will add the feature 1/4, and certainly have certain place we still need to add the the feature there is the mass adjustment for fine topography. Right now we are using the coarse resolution topography on the edge, the blending zone. Then certainly the code still need optimization to improve the efficiency on the high performance computer. Another aspect we put a lot of effort in next year is put the new data, how to get the more new data into the model, especially in the core area. Then the second part is we try to create the atmosphere ocean coupled DA model. Right now, our strategy is use the weekly coupling, and gradually everyone is going to transition, the UFS community transition to JDA. So we are also have the plan to transition, develop the infrastructure so that the other researcher can test that infrastructure. And the physics part, we focus on PBL. When some big impact, the PBL we know that impacted TC intensity a lot. Then also we focus on the land part, the NOAA MP, that is after storm landfall. That's much more impact, especially the inland flooding and other aspect. Then the convection scheme, we are still testing different convection scheme. The models still have some kind of bias. That's probably related to the convection parameterization. So we are testing and upgrade our current convection parameterization. And microphysics, certainly when we have the cloud resolved model, microphysics is going to dominate the thermodynamics processes and the precipitation processes. So microphysics parameterization, we are work on that to upgrade. Ocean part, right now we are using HICOM. It's aligned with the operational model. They're going to transition to MOM6 global. Then we're also transition to MOM6 regional. So that is the work we are working on that, and we almost close. We're very close to finish this part, but this will implement into the model, and for the evaluation and the test. The ensemble capability right now, the model itself for fixed domain is working, but for the moving nest, we still develop that capability, especially the stochastic physics ensemble capability. We are working on that, and we plan to put the ensemble on cloud computer that will give us some advantage to have more members can run, because the current NOAA HPC is not able to satisfy our HPC needs. And certainly for any model, once we create the model, the products become so important so that forecaster and the researchers can use our model. So that's, we focus on these three aspects: the ensemble, products, and the products fidelity. Sometimes our products, the forecaster and the researchers, they just ignore because they think that's not very reliable. So we still work on those products. Then also, right now we are running the model 5 days. In the future, we'll run 7 days. So the product 7 days products also need to develop. Next slide. Then further down, after 2024 season, we will continue and develop the model capability. So especially the global moving nest, that probably down the street we're gonna gradually move into the global framework. And also another capability we are inspired by a lot of researcher needs is develop the large eddy simulation capability. That is under our plan to work on that, and we have some collaborators already start work on that. And for DA part, right now everyone here there's a lot of AI technology available for us. So that's one of the options for us to use that technology for DA. That part we still haven't started yet, but we are in the next few years we're gonna develop that kind of capability. Then the ocean coupling, I just mentioned the weakly coupling compared to the strong coupling, that is still we need to evaluate which way is the better way. So our sky radiance right now, the DA in the DA side, the radiance they use CRTM, but in the model we use RTM. So what is the controls between these two? We need to still evaluate whether we want to unify this, especially our model use CRTM, but at this moment we haven't do this test yet. The new DA methodology right now, you have several projects support that, especially the scale aware capability and the particle filter capability that is in the in several projects they have developed that capability, and it's in the near future they move to the transition. The DA and the physics parameterization interaction, that is always our uncertainty. When we change the physics, can we use the exactly same DA method? That's also need a test and evaluation. The observation part, we have more observation data, especially the new technology come to us, like the USA, like the cell drone, all these new data come in. How can we use that? That is another aspect we are exploring. And the observation strategy, we have G3, G4 to fly into the hurricane, but how to sample the data, how to collect the data more effective, that is still we are testing with the new model capability. We can use that new model to test the effectiveness of the observation. Ensemble, right now we are focused on the physics ensemble, but another one we can do is initial condition perturbation. We haven't done that part yet. And certainly ensemble for DA and ensemble on cloud will continue work on that. The physics part, we have some project to use AI technology to develop the physics parameterization, and also the project to work on the sub-kilometer physics, especially the TKE part, the physics interaction part. That is another uncertainty in our model. When we switch one package to another package, can we really couple them together? Our physics couple them together. And the ocean wave atmosphere three-way coupling, that is already available in our model, but we didn't totally switch all the two-way interaction, especially the ocean wave atmosphere is wave atmosphere is only one way. Ocean wave, there's no interaction yet. So all these capability already there, but we haven't switched on to test the effective. Then the ocean wave model physics, it's not, we're not focused on that aspect yet. Right now we focus on the atmospheric component, but the future we also will move to those aspects. Then the model is initialization. Certainly, it's always a challenge for ocean part, but we continue to work on that with more technology, more data coming in. And
Hello, Xiujing.
Zhuzhen, you're on mute.
okay, Zach, click one more. Yeah, so we have third nest there. So the telescope nest capability let us have the ability to down to the large area simulation resolution. So that's the capability we are testing and work on that. Next slide. Okay, we have another effort is doing the multiple stone. That is the multiple stone look like, because our previous research find that the multiple stone, if we focus on one stone, then that will compared to the multiple stone interaction, we have more capability with more fitting into the reality. The science part we can prove that the multiple stone have more effective and can improve the future forecast. Next slide. So here's the summary for this. The target yearly upgrade is still going on. So so every year we will have one version upgrade. Then the convection result model resolutions, we will continue to move that. The future is just like Zach said, the future will be 1.8 for the nest domain, the moving nest domain. Then the multi-member HAFS ensemble, we still work on HAFS A, HAFS B, and we try to get as much as possible the differences of the physics of the initialization. All these is meets the requirement of the operational center. They want 2 intensity model to configure their consensus model. Then we also merge hurricane forecast system, the HAFS system with the GFS system. We want to sync as much as possible. They have the physics, the infrastructure, everything sync with them, so that we have still take advantage of the UFS unified framework. The next one is to develop the LES capability. Certainly, that is really important for dynamics and physics development, especially when we use the AI technology for the physics parameterization. The LES is really powerful tool for us to generate the data. The future release also, the release is one of the priority in the next year, the whole FY 2024. The reason is we want community use it, and we want a community feedback. With that, I want to take Zach, and I want take any question from you. Sorry, we're a little bit late, but I would like you give us feedback and ask us questions, hard question.
Thank you. Yes, I'm going to go ahead and take back the screen, and I'm going to show the, I don't think I'm showing the correct screen, am I? Okay. I'm going to show the questions document, and you all can go ahead and read off the questions and answer them.
That's the first question. Do you want to answer that?
Yes. Let me read it. The two HAFS physics suite configurations and relevant workflows included or planned to be.
Answer is yes.
Yes. The answer is definitely yes. We want to publicly release actually basically included 2 configurations, the four blow of model configurations, both HAFS A and HAFS B. Including
the second question is all developer, if you have a project with us with NOAA, you can access our GitHub developed version. But for the public release, especially you don't have any project with NOAA yet, we are planning, the next 6 months, we are planning when we close to the date, we probably have much better idea when available to the university researchers. We want you to use the model and use as much as possible. And certainly that is our intention to release the model. And we also want you, give us feedback and contribute to our development. The third question. Not yet. That the third question, the post landfall and flooding that you just mentioned with NOAA MP will be coupled with hydrology model yet? No, not yet. We haven't think about the hydrology model coupling yet, but definitely we can provide the necessary input for hydrology model.
And regarding question 2 about the latest HWolf release on DTC, actually, yes, DTC is actually in the transition period to transition the hurricane modeling support to EPIC. So the latest model, I think we are dealing with some of the issues in the DTC release right now. But if you can send us the DTC help desk, we can help you to, I mean, at least for the NOAA RDHPC machines, we can work with you to make it work. The HAFS latest release.
By the way, this one is a question more related to HWolf. I don't know if that is mistype of the HWolf HAFS.
Yes, it is. I think it is related to HWolf. Yes, I think.
Okay. Yeah. So I think the HWolf parts, the support funding is running out. So I don't think you can get a substantial support for HWolf.
So that we can deal with like case by case, but in general, yes, DTC is transitioning the support to EPIC.
Yeah, but they are not transitioning the HWolf support. HWolf support is going to, you know,
basically face away.
Diminish
yes.
fairly quickly. Yeah.
Okay.
So I will encourage to, you know, contact us, because right now the help desk, HWolf help desk also discontinued. So you only have the phone there. So it's not you're probably not able to get to your answer quickly. But the main things I would say, prepare the transition to HAFS in the near future.
Okay, great. Well, if there are no questions, that will wrap us up. Thank you so much to Zach and Juzhen and Dr. Vijay for helping us today to give our presentation and to give our introductions. Thank you all for attending this webinar. We really appreciate it. Our next webinar is going to be held August 10th, 2023. So please join us. We look forward to seeing you then. Take care.